All right, guys, so today we're going to talk about solving what we call a linear quadratic system. In grade 10, you guys solved linear systems, so I'll just remind you kind of what that was all about. So you guys figured if you have two lines that are both on the same graph, I could have two lines that cross just normally, and I would get 1 point of intersection. So we say when we're solving a linear system, we're looking for the number of points of intersection, and then we solve for the point of intersection. What are other options for how linear systems can intersect? Does anyone remember? Kira?
They can be like the same line, so they intersect like always.
Right, so if I have two lines that are essentially the same, okay, they overlap each other, so they actually intersect everywhere. So we would say infinite points of intersection here. Okay, we call this parallel coincident because they're parallel and also the same line. Okay, and then there's one other option that we could have. Parallel and what we would call distinct because they don't overlap. So let's say we have a line like this and a line that's parallel. These lines will never cross. So in this scenario, we would have 0 points of intersection. Okay, so today we're going to explore a linear quadratic system. So one line and one parabola on the same graph. So I'm interested if you guys can figure out with the person sitting next to you a couple different options for how one line can intersect one quadratic on the same graph. So what are the options for number of points of intersection? So for lines, we can have 1, 0, or infinite. I'm curious if we can figure out what the options are for a line and a quadratic. So see if you guys can figure that out. I'll give you a couple minutes. All right, so what did you guys figure out? What possibilities are there for how a quadratic and a line can intersect? Give me one possibility. Kira?
So once if it's a vertical line.
Okay, so we could have like a quadratic, let's say, and maybe like a line that cuts right through it, right? Like so?
Yeah.
So this is a possibility for what we could have. That would be 1 point of intersection. There's also another way that we can have a point of intersection, and you may see this word used in some future questions. So we can have 1 point of intersection like that, or I can also have, let's say I have my quadratic here. I can also have a line that kind of like skims the outside of a quadratic exactly at one single point. So it like just crosses just at that one single point. So that would be another way that we could have 1 point of intersection. When we have a line like this, we call this a tangent line. Okay, so you may see the word tangent or tangent line used in some examples on your worksheet. So basically it just means it has 1 point of intersection with the quadratic. So both of these options are 1 point of intersection. Okay, other options. How else could a line and a quadratic intersect? Sophia?
So like 2 points. So
Yeah.
one of them
Mm-hmm.
and then
Yeah. Yeah, it could be like horizontal or it could be diagonal, right? As long as it's cutting directly through the quadratic, that would give us 2 points of intersection. Okay, any other options for how a line and a quadratic can intersect? Vanessa?
they could have 0 points of intersection if it's like a horizontal line above the maximum or below it.
Yes, exactly. So I could have something like this, and then maybe I have a quadratic opening downward. So maybe I have something, oops, that was bad. Maybe I have something like this, right? So that would give me 0 points of intersection. Are there any other options that we're missing here? Could we have infinite between a line and a quadratic? That's never really going to happen. A parabola is a curve and a line is obviously straight, so those are never going to overlap each other more than either once or twice. Okay, so those are the options. We could have one point of intersection, two, or none. Okay, so when you see solve a system of equations, essentially what we're looking for is the actual xy coordinate of the point or points of intersection. So when we deal with a linear quadratic system, here's a couple steps for you guys to kind of get you going on how to solve these types of things. Essentially what we're going to do is kind of like the substitution method that we used in grade 10. So you guys remember when you solved linear systems, you did substitution or elimination. We are going to kind of like substitute the line into the equation for the quadratic. We're going to set them equal to one another. And then we're going to move all the terms to one side, and you're going to get something that looks just like a normal quadratic after you do that. So we can either solve that kind of normal looking quadratic by factoring, and if we can't factor, then we'll use the quadratic formula, just like we always do with quadratics. And then we need to find their y coordinates. So once you get your x's, you're going to sub back into one of the two original equations, find your y's, and state the xy coordinates of the points of intersection. Okay? So this is all well and good, but it sounds kind of confusing when we're not actually applying it, right? Okay, so let's take a look at an actual example here. Okay, there's also just like a little side note here. If you complete steps 1 and 2 here, you can actually predict the number of points of intersection, similar to how we predict x-intercepts for a quadratic. And basically, we just use the regular discriminant, b squared minus 4ac. If it's positive, we get 2 points of intersection. If it's equal to 0, we get 1 point of intersection. If it's negative, we have no points of intersection. We'll essentially stop the question there if we don't have any, because there's nothing to solve for. Okay, so we're going to do a prediction here. That means that we have to set these equations equal to one another. So we have basically y equals and y equals, and we're subbing one equation into the other equation. So set the equation of the line equal to the equation of the quadratic. Why does this make sense if we're trying to find a point of intersection? Why should I set the two equations equal to one another? Lisa?
Their point is going to be the same.
So at a point of intersection, the xy coordinate of both equations is equal or the same, right? So it should make sense if I'm trying to find out where they cross or have an equal x and y value, that I set their equations equal to one another to find out where they're equal, right? Okay, so that's step number 1. Step number 2, we're going to move everything to one side. So I'm going to move the 2x and the negative 5 over. And we're just going to gather up all the like terms. Okay, we're going to do a quick little prediction here. Now that this kind of looks like a normal quadratic, even though we know that it's not, we know that it's a combination of a linear and quadratic function, but we still can use b squared minus 4ac. That gives us some information. So in this case, a is 1, b is negative 9, c is negative 10. We're going to plug them in. And just see what we get here. So I think we're getting 81 for the first part, plus 40 for the second part, so 121. So is this positive, negative, equal to 0? Okay, so a positive value is this first scenario. That means we have 2 points of intersection. So this is not roots anymore because we're talking about what we're actually finding here is where the line crosses the quadratic. So we can say, therefore, 2 points of intersection. If I get 0 at that point, I'm done. I'm not going to try to solve for something that doesn't exist, right? So that's the benefit of checking first. Okay, and then for part B, it asks us to find the points of intersection. So we're going to work off of what we just did for part A. So I'm going to work off of this x squared minus 9x minus 10. And we're going to solve this similar to how we solve a normal quadratic. So our options are we can factor. I'm going to say you should factor wherever possible because it's just a lot quicker than using quadratic formula. But if you can't factor, you have to use quadratic formula. But are there any two things that multiply to negative 10 and add to negative 9? No? Millie, do you have something? Yeah, that actually works. So multiplies to the negative 10, adds to negative 9. Negative 10 and 1 work. And this is a quadratic where the a value is equal to 1, so we can just put these right in brackets right away. Okay, no use doing more work than I need to. So what are our x's equal to here? Okay, it's similar to x-intercepts, right? So here x equals 10, and here x equals negative 1. Okay, these are not x-intercepts. These are the x-coordinates of the points of intersection where the line crosses the parabola. So what I need to do is I need to sub these x's back into one of these two functions. It doesn't matter which one I choose because they should both, if I found the correct x's, they should both have the same y-coordinate. That's where they cross, right? So I usually personally sub into the line because it's just a simpler equation. But you can certainly plug into the quadratic as well, and you'll find your y-coordinate. So we're going to evaluate f at 10 and f at negative 1. Okay, so for the first one, we get 15. And we will also evaluate f at negative 1. Again, you can also do w at 10 and w at negative 1. You should get the same answers as for when we plug it into the line. So final points of intersection, each one has an xy coordinate. It's 10, 15, and negative 1, negative 7. Okay, we call these the solutions to the linear quadratic system. Any questions for this one, Lisa?
What would your answer look like if you were not?
Then you would just be writing like just the 1 point as your point of intersection. That will never, you always, in order to solve a linear quadratic system, you need to be given a line and a quadratic. So you're always going to be given two equations here. If you're solving just something like this, then you're just factoring. Like if you're solving for the roots or whatever, then you're just factoring to solve. You can, but I did this in one step. I ideally do not want to use quadratic formula where it has like multiple steps in order to just find out at the end that I could have factored it in like 1 quick second, right?
But it's the same thing.
Yeah, but we are looking for most efficient, right? If I spend all the time on the test like plugging into the quadratic formula, I'm probably not going to have enough time to finish when I could just do this in like 10 seconds, right? Or maybe a minute. Okay, let's try one more. Okay, so we're going to make a prediction and then we're going to find the actual points of intersection here. So first step, we are going to figure out where these two equations cross one another or have points of intersection by setting them equal. Okay, kind of like using substitution. Okay, we can bring these over. Okay. Quick little trick. If you don't want to have to deal with this, you're just going to multiply every term by the denominator to eliminate that fraction. So I'm going to multiply each term by 2. Same with the 0 even. And then what happens with the first term here is these actually cancel. So I'm just left with a regular x squared there. Minus 4x plus 4 equals 0. Okay, I just made my life like 10 times easier right there. Okay, so we're going to do a little prediction. For part A, where we sub in b squared minus 4ac. Oh. So b here is negative 4. A is 1 and C is positive 4. We'll get 16 minus 16, so that gives us 0 for the discriminant. What does this tell us? Andrew, what? Yes, therefore we have 1 point of intersection. Perfect. Okay, so let's work off this. We have 2 options. If we can factor, we'll try to do that. If not, then we will use quadratic formula. So 2 things that multiply to 4 and add to negative 4. Negative 2 and negative 2. So just x minus 2 and x minus 2. So that's actually the same bracket, right? So this actually was a perfect square trinomial. If you had noticed that, you could have used that perfect square trinomial quick factoring. If not, no worries. So here, what do we get from this? X equals 2. That's right. Okay, so the x coordinate is 2. We are going to plug this back into either f at x or g at x, so one of the 2 original equations, in order to find the y coordinate. So I personally prefer, I'm going to do g at 2. If you want, you can test it in f at 2 and see what you get. So final point of intersection here is 2, negative 2. And there's 1, just as we predicted.
How do you get from like the, now you have nothing, then you know that x squared is 2, x minus 2?
So this is what we're looking at here. So we're factoring. So we're looking for 2 things that multiply to 4 and add to negative 4. So once we find the 2 numbers here, we can put them right in brackets. Okay, that's only possible when we have a 1 in front of the x squared. Otherwise, we're doing that other factoring, that like x factoring method that I showed you guys. Any other questions on this one? We're okay? Okay. The other type of question that you might see is you might be given some information about the line and told about the number of points of intersection. So in this case, we have a line with a slope of 4, and we know that it intersects the quadratic function f at x with 1 point of intersection. It asks what the y-intercept is of the line. So you might see it asked like this, 1 point of intersection with the quadratic, or you might see is tangent or is a tangent to the quadratic. And basically that means the same thing. When we see the word is tangent to the quadratic, it basically just means that we have a line like this that is skimming the quadratic at 1 point of intersection. So if you see the word tangent, you want to think 1 point of intersection. Okay? Okay, so here's what we know. We know we have a line with some slope of 4. So if we think about a line in terms of y equals mx plus b, we know that m here is 4. And the b value is actually the y-intercept of the line. So that's actually what we're looking for. So right now that's the question mark. So b is actually not an ideal variable for this because once we are working with a quadratic, then it might get confusing between like a, b, and c of the quadratic. So I might suggest that instead of using b, we use a different variable. Okay? Maybe we'll use like k or something like that. Okay, I just don't want it to get confusing with the a, b, and c that we use for discriminant. Okay, so we'll let that be k. You can let it be anything, just don't let it be a, b, c, or x, ideally, or y. Okay, so we're going to set the two functions equal to one another, just as we normally do. We're going to move everything to one side, so we're going to follow steps 1 and 2 as usual. Move everything to one side, simplify where you can. And one thing that you should keep in mind is that the b value in a line, like when we have y equals mx plus b, that's a constant value. What do I mean by constant value? Yeah, there's no variable with it. So when I move this k over, I'm actually going to group it with the -8 because those two things are both constants. So it'll be like -8 minus k. And then we can gather the like terms here. So this is kind of like our a, b, and this together is like c. Okay, the question also tells us another piece of information. It tells us we have 1 point of intersection. So we know that b squared minus 4ac must be equal to 0 if we have 1 point of intersection, right? And we have an a, b, and c here. So let's see what happens when we plug in that a, b, and c. All right, we're going to simplify a little bit here. -2 squared is 4. What is half of 4? 2. So I'm going to write -2 there. Okay, so just simplifying this to -2. Okay, and then this -2, we're going to bring that into the bracket. I have a whole equation and I only have one variable in there. I should be able to solve for that variable. I can get k by itself, right? We can solve for that. Okay, so just isolating for k, we're going to get it alone on one side. We're going to bring the 20 over. We'll get negative 20 and divide out the 2. And we get k equals negative 10. That's the y-intercept. We just found it, right? Because we let our y-intercept be k. So our y-intercept is 10. So that would be the point 0, negative 10. Okay, so you're going to follow steps 1 and 2 as usual. Set the equations equal to one another, move everything over. And then in the case where you have like the tangent or one point of intersection, you're going to plug in your a, b, and c into the discriminant, set it equal to 0 because of one point of intersection, and just solve for the variable. Any questions on this one? Okay, if you notice, these are actually the same two equations that we just worked with above. So we got negative 10 as the y-intercept, and that was actually the line from up here, 4x minus 10. So I just asked the question in a slightly different way. Ainsley?
For you specifically, when we get the answer to our questions, do you want us to do the both or something every time?
I don't need to. You can just say like 0, negative 10. That's fine. If it were like a word problem that needs like interpretation, you could say therefore, but. Lisa? Yeah, so when you think about like a line in y equals mx plus b format, usually it's like, let's say 2x minus 7 or something like that. This is the y-intercept, right? It's what we call a constant. So it's a number without a variable. So I know that this is going to be a number without a variable, so I'm grouping it with the other number without a variable. So I'm grouping the constants together. Does that make sense? Okay. Okay.